Alrighty, so today we're looking at limits at infinity, and we're going to kind of revisit the idea of limits, looking at when they blow up and what their long run behavior is, and then what we can do when things get what we call indeterminate. Now that we have the power of the derivative, this application is available to us. So let's jump right in. Again, I've said that limits are the underpinning of calculus. And hopefully you remember that they were pivotal in the definition of the derivative, right? In kind of bringing that shrink wrapper of the slopes of the tangent of the slopes of the secant lines down to the slope of the tangent line. But they're also critical in the upcoming definition of the integral, which is one of the last things we look at. But also just describing what's happening in the short run. Call the short run behavior, and defining continuity, right? They're critical there. Continuity, as well as a long run behavior. Or you can call it the trend, right? If there is a long run trend, limit would the long run limit would define this. And so, again, what is the meaning of a limit? It's kind of what do we say? Like our best guess for where a function is heading. All right, it's very different from actually taking on a value, right? We're talking about this notion of approaching. So when we're talking about infinite limits, we have two different kinds. One is that a limit at a point blows up, so blasts off to infinity. Or there's the other idea of an infinite limit, which is that we let the input run to plus or minus infinity and see if the function has a trend or not. And if it does, this is what we would call a horizontal asymptote, which is most likely something you've heard before. If the function has a trend, some y equals k, some constant, that means that after a while, this is my function here, as x increases, it's approaching this trend line of y equals k and not really straying from that. It can actually cross the horizontal asymptote, which is different from a vertical asymptote, which is where a function blows up. And so we've seen this before in this form where, maybe you've got something where at x equals a, there's a vertical asymptote, there's an unremovable discontinuity. And so the function might do something like this, where we've got this vertical asymptote. This is an asymptote that the function cannot cross because it's not defined there, or there's a discontinuity of some kind. So these are the two kind of flavors of infinite limits. A lot of times we can resolve these just using algebra or rewriting them, but now that we're armed with the derivative, we've got a bit more, a bigger tool in the toolbox to use, especially for more interesting limits and a function that kind of blends two types of patterns, whether it be exponential in power functions, trigonometric in power functions, etc. All right, so something that we've run across kind of already is looking at a rational function. X is approaching 1, let's say, and we've got this rational function on the right. We want to know what the limit is. Well, we can see if we just plugged in 1, you'd get 0 over 0, and kind of a rookie mistake would be to say, well, this limit doesn't exist, it's indeterminate. We can actually do a bit more just by knowing that this has a type of discontinuity that we're comfortable with and where the limit still exists. So if we take the limit as x goes to 1 of this rational function, if we massage it a little bit with some algebra, we see that the top is actually x minus 2 times x minus 1 all over x plus 1 times x minus 1. And what this allows us to do is say, well, everywhere except for 1, this thing is equal to having these factors canceled out. And since the limit doesn't actually go there, this is fine to do. So this actually becomes the limit as x approaches 1 of x minus 2 over x plus 1, which is what, negative a half. Okay. So this is not so bad. Again, this should look relatively familiar, but we can come across things that maybe it wouldn't be so nice. And you might see something like, maybe if this was a plus 3x on top. Okay, now when you come across this and you try to factor this into, all right, well, this is x plus 2 times x plus 1 all over x plus 1 times x minus 1. Well, now that problem in the bottom can't be factored out anymore, right? And so we end up getting, what, 3 plus 2, 5 over 0, which blows up, okay? And so this blows up to positive infinity, okay? And it actually blows up to both sides of infinity. Let's pull up a graph real quick. Okay, so we see we have a vertical asymptote here at x equals 1. See, as we approach it from the left, it shoots down to negative infinity, and as we approach it from the right, it blasts off to positive infinity. Okay, so this is a place where we have a limit that blows up. So the very quick lesson here was, sometimes with a little bit of algebra, you can resolve a limit that looks like it might blow up or not be defined. Sometimes you can't. All right, and so that's why we're going to develop another powerful tool here in a bit. The other type of infinite limit, remember the other flavor I said, was letting the input run forever and see what happens. Now, there's two ways to kind of think of this. One, I think, is the more intuitive way, which is that of using the idea of dominance of power functions. Which means that, x to the n power will dominate x to the m when n is greater than m. And what do we mean by dominate? It means it like wins the race, okay? That if you let the input run off to huge numbers and you let x to the m be on the top and x to the n be on the bottom, that this will be 0. I'll put this over here because this is really the limit as x goes to infinity of x to the m minus n. And if n is bigger than m, then this is a negative number, right? Or this is a negative exponent. And if this is a negative exponent, this is really in the denominator, and so it's eventually going to go to 0. So that's how we show dominance. So why do I say this? Because if we take a look at our limit as x goes to infinity of x squared minus 3x plus 2 all over x squared minus 1. Now this is different, right? We're not zooming in at x equals 1. We're letting this go out to the long run. And we want to see what happens. So using this idea, we say, well, x to the n dominates x to the m when n is greater than m, and especially at large values. So as x gets large, we say, these numbers, these x squared terms, start to very much not care what, especially this plus 2 is doing, right? Imagine 10 billion squared plus 2. It's barely a difference at all. Minus 3x Also, we don't care about this term because x squared will dominate this 3x in the long run. So as x gets large, we start to care about just the leading terms. Only leading terms, are steering the ship since they dominate. Okay, and so what does this mean? It means we can say as x gets large, so the limit as x goes to infinity of we can say becomes the limit as x goes to infinity of x squared over x squared. We can kind of ignore these other terms because they're not contributing as much as these huge numbers being squared. And then, of course, we see looking at this, well, this is really just the same as the limit as x goes to infinity of 1, which is just 1. It's a constant limit. Another way that you can think about this is that you've got these two racing terms in the top and bottom, x squared and x squared, and their ratio, their coefficients are 1 and 1. And so since they're kind of tied for first place, the trend will be the ratio of the coefficients. And here that is 1. Okay. If 1 was weighted a little higher, if this were 4x squared up here, this limit would be 4 over 1 because you'd know these terms would cancel and you'd be left with 4. Okay, I'm not going to muddy the water here, but just wanted to say that. So this is a long run. How can you tell? Because it's going off to infinity. And if it's two rational functions, you might be able to use this dominance argument to prove it. I'm going to show you the other way to tackle this limit right now as well, which also might come in handy. Okay, so the other way to handle this would be to see, all right, yes, you have two power functions vying for dominance, and what we're going to do is this fancy mathematician's trick, which is to divide both the top and bottom by the same thing, thereby, in a cheeky way, not really doing anything to it, but massaging it into something more useful. So we say this is the limit of 1 over x squared over 1 over x squared times what we had inside, to then kind of get us to this better place. So if I distribute that through on the top, this is the limit as x goes to infinity of, everything's being divided by x squared. So it's 1 minus 3 over x plus 2 over x squared in the top over, x squared over x squared is 1 minus 1 over x squared. Now, why is this helpful to view? Well, now we can see, really what's happening, which is when x races off to infinity, we know that a constant term is going to be dominated by this power function. Same here and same here. These are all going to 0. And so then you'll just be left with the limit as x goes to infinity of 1. I mean, we could break this up a little bit, but we can just say that this is equal to 1 because it's equal to 1 over 1. All right. So here we have just another method. And again, to clearly call out what that method was, it's to take the highest power in the top and bottom and do this multiplying by a fancy 1 trick to get it to a place where you can come up with a more definitive limit. Okay, so 2 ways to go about it. Usually when it's just 2 rational functions like this, it's not too challenging. So what is challenging is when you have a limit that is an indeterminate form and there isn't much algebra that you can do to resolve it. So the gentleman who came up with this was a French mathematician by the name of Lhopital. You'll see all different kinds of crazy spellings and accents on this name wherever you read. It's always different. So, but you'll pretty much always get the gist that this is L'Hopital's rule. This is what he was known for. Um, and so it's used to resolve indeterminate forms of 0 over 0 or infinity over infinity. So the rule states that if you've got this, that the limit of f and g is either 0 or plus and minus infinity, and that g prime of x equals 0 does not equal 0 except possibly near the point that we care about, then what we see is that the limit of f over g is equal to the limit of their derivatives over each other, which is not really intuitive, but I'll give you a quick explanation as to why that works. All right, so roll with me for a sketch here. So if we zoom in on a point, let's call it, C, and I've got my two curves, f and g, all right, because again, we're thinking about the ratio of these two functions. So let's say they pass through this point x equals c. Here's f, here's g. Remember, when we zoom in on differentiable functions, they look like lines. So these could go off and do crazy things, but at this point, we're so zoomed in that they look like lines. Okay, that's key to remember. So then at some point away here, we'll call this x. This quantity here, we could call this, right, that tangent line approximation of the g prime at c, the derivatives value at c, times x minus c. And again, to understand this, this is just the slope, the rate of change at this point, times the little nudge in the input that will give you the height, right? And then likewise over here, this height would be f prime at c times x minus c. And the nudge on the function f over this little change in the interval. So what is this telling us? This is telling us that the change close to this point, that as we get close to c, the ratio of f over g, so these heights of the functions, since they look like lines, can really be taken to be the slopes of their tangent lines, or the derivatives of f and g. Okay, so again, just because we're in so close here, the heights become very, very close to the slopes. All right, and that's the idea of linear approximation. So we're going to let this drive L'Hopital's rule. So I'll show you with a quick example here too. So if I'm given this limit to calculate, e to the 2x minus 1 over x, there's no real algebra I can do to dance this thing out of the fact that it's going to, an indeterminate form of 0 over 0. And actually, I wrote this down wrong. This minus 1 should be here. Let me do this. Should be out here, because that wouldn't be indeterminate the way it was written. Okay, so this minus 1 is just another term in the top. So this here, if I let x go to 0, this term would become 1. I'd have 1 over 1 minus 1 over 0, and so this would be indeterminate. So of the form 0 over 0. So when it's this case, we know that g prime of x, this base here, isn't 0 everywhere. Then L'Hopital's rule applies, because we see, okay, it's of this form. Oops. We see it's of this form. We see this is the case. Then we can apply this rule. All right. And the reason that this works too, I'll share here that e to the minus 2x minus 1 over x. When we let x go close to 0, we are letting f approach and G approach their local linearization, right? When we zoom in really, really close. So F starts to look a lot like its derivative. G starts to look a lot like its derivative. And so, that the slope of the tangent line of this, let me use a different color. The slope of the tangent line of F here is 2x, and you can verify this yourself near x equals 0 if you did the local linearization. And for the simple line function y equals x, its tangent line approximation is also just x. And so we know that this here can be simplified to just 2 over 1. And this is equal to f prime of 0 over g prime of 0. Which again, since this is a kind of a removable discontinuity, we can state this in a more general way for the rule that this is the limit as x approaches 0 of f prime of x over g prime of x. So just kind of demonstrating why this works. So this is the y. So, but in practice, really what you do, you wouldn't have to go through this whole rigmarole. You would just say, all right, since this is of the form 0 over 0, this tells us that the limit as x approaches 0 of f over g is equal to the limit as x approaches 0, and then just take the derivative. So this would be, 2e to the 2x over 1, and then you let x go to 0, and you get 2 times 1 in the top. Let me zoom in here. 2e to the 0 over 1, which is really just 2. Okay, so you get to the same place. But this was kind of the linearization argument down here. But this is how you'd apply it in practice. So let's do a couple more examples here. Showing another limit that we've looked at before as being, somewhat mysterious, kind of bending our understanding of algebra. But with L'Hopital's rule, we can see, first of all right, yes, this is of the form 0 over 0, so that applies. We see that g prime of x isn't 0 everywhere, isn't what we call identically 0. And so then what we can do then is apply L'Hopital's rule. Equals the limit as x approaches 0 of cos x over 1. And, if you're showing your work here, you might, kind of comment here. We're applying L'Hopital's rule so that and I know what we're doing. And then here you have no continuity issues. You let x go to 0. As cos approaches 0, we know that this approaches 1 over 1, which is 1. That's a lot easier of an argument than we were dealing with the last time we saw this limit. But it's kind of the power of L'Hopital's rule. As long as things can be worked out a bit and these conditions are met, then you're good to go. So again, the idea is since we're working with infinity, a lot of things are not intuitive, and so we're going to need this kind of advanced technology to help us with certain problems. It is also helpful in showing us what we call dominance, so comparing different types of functions as to their long-run behavior. So we'll walk through this example really quick. Okay, so again, what we can do is to show something dominates it is to show that it races to infinity faster than the other functions. So what we would like to do then is show that the limit as x goes to infinity of ln x over x to the 1/2 is 0, because that would show us that x to the 1/2 is blasting off faster than ln x can keep up with, and this whole thing will go to 0. Okay, so again, this could be complicated, but with the fact that we know that this is of the form infinity over infinity, right? Because ln x is blasting off to infinity, and so is x to the 1/2. Again, the rookie mistake would be to say, well, there is no limit here. But that's actually incorrect because, as you'll come to see if you go further and further in math, there's different sizes of infinity. There's different levels of infinity. It's not just one thing. So this is of this indeterminate form. And we know that g prime of x isn't 0. So we can apply L'Hopital's. All right, so we go ahead and do that. We say that this then is equal to the limit as x approaches infinity of 1 over x in the top over 1/2 x to the minus 1/2 in the bottom. And with some algebra, I'll pull this 1/2 out. It becomes a 2 in front. And so this becomes x to the 1/2, or x to the minus 1, sorry, minus negative 1/2, so that's plus 1/2, which then becomes 2 times the limit as x goes to infinity of x to the negative 1/2. And so if I write this again as 1 over x to the 1/2, you'll see that this is clearly 0. 2 times 0, which is 0, because as x increases without bound in the base, and 1 is just staying put in the top, this thing drops to 0. So this is how we show that the square root of x actually dominates the natural log of x, which is not clear in the short run, and we can say this very definitively now, armed with L'Hopital's rule. Okay. You can do this with all sorts of functions, comparing exponentials to power functions, etc. But we're not going to do all that today. Wanted to do 2 more. Here's an example of where you apply L'Hopital's rule, but you don't win right away. And let's see what I mean about that. So you can see that this is of the type infinity over infinity. And so we want to take the limit x squared over e to the x. We see L'Hopital's rule applies, so we go ahead and we apply it. And we get 2x over e to the x, and you say, well, dang, that didn't really solve my problem because this thing's still going to blow up and this thing's still going to blow up, but I don't know how fast. Well, the good news is L'Hopital's rule still applies because this is still of the form infinity over infinity. So then you apply L'Hopital's rule again, and you get 2 over e to the x, which then is 2 over infinity, which heads to 0. Okay, so you apply L'Hopital's rule once. That didn't quite work out. You can apply it again. There may be times where you need to keep doing that, and you will eventually get to some result. As long as you can show that the conditions apply to use the rule, you can use the rule. So I'd call that like one advanced use of the rule, or kind of extending it a bit. The other would be to recognize when a limit is not in form to use L'Hopital's rule, but you can get it there to use it. So sometimes it's simple algebra, sometimes it's a little bit more intense. So if we look at the limit as x goes to infinity of x e to the minus x, we see this is of the form infinity times 0. And so this is an indeterminate form, right? Something's going to 0, something's going to infinity, but it's not in the form, ready-made to use L'Hopital's rule. So what do? Well, we want to get this to a place where either it's 0 over 0 or infinity over infinity. And we know that, 1 over 0 is infinity. Again, I'm using quotes because this is not real math. These are like, shorthand conventions. We know that 1 over 0 blows up. So if you have something that's 0, can you write it as its reciprocal? And so we do rewrite this using the fact that it's got a negative exponent. We can rewrite this as x over e to the x. And then what do we see? Well, now I'm of the form infinity over infinity. So now I can apply L'Hopital's rule. I get 1 over e to the x, and I know that this is equal to 0. Okay, so again, this is a simpler example on how to massage it into form. But first, this piece is key in noticing what form it is in now, and then driving it into one of these workable forms. So I want to do one that's a little bit more challenging, because I know algebra is usually the place that we struggle the most. And again, I say that from a place of understanding and not of judgment. That's the hardest part of this course. So here's another example. Yeah, let's do this one. Calculate the limit as x goes to 0 of 1 over x minus 1 over sine x. Okay, and I also won't pretend that these are obvious. This is something that we learn how to do. We learn how to massage expressions into things that work out. It's not just something you should see straight away. So, okay, so we see that this is of the form when I take the limit, if I just, plugged in 0 here, I can't do it, because what would I get? I'd get infinity minus infinity, right? Because this is really of the form 1 over 0 minus 1 over 0. So I can't really work with that. But what I can do, I've got these two fractions. Maybe I bring them together and see what happens. Okay, so how do you bring these things together? Well, you multiply each term by, why don't I write it out? I'll be super nice. Minus x over x times 1 over sine x, right? Get common denominators and combine. So this is the limit as x goes to 0 of sine x minus x over x sine x. Okay, and then from here, this is something that we can apply L'Hopital's rule to. We see that as x goes to 0, this is now of the form 0 over 0. So now we can apply L'Hopital's rule. And so we go ahead and do that. And so we see this is equal to then the limit as x goes to 0 of cos x minus 1 over, in the bottom we're going to have a product rule, so it'll be sine x plus what? Plus x cos x. And this doesn't quite do it, because as I let x go to 0, the top is still 0, and the bottom is still 0. So I apply it again. See if it gets any nicer. So the derivative of the top is just going to be negative sine x, right? That 1 drops off. Derivative in the bottom, sine becomes cos. I have a product rule again. So that's cos x minus x sine x in the bottom. So this will be 2 cos x, just to kind of neaten this up a little bit. And so from here, what do we see? If I let x go to 0, then I'll be left with, well, sine of 0 is 0 over 1 minus 0. So that's all 0. It's not indeterminate at all. We know it's heading to 0. So here we applied L'Hopital's rule once, L'Hopital's rule twice, and it worked out after some massage. I don't love that term, but manipulate, whatever you got to do to get it into a form that's workable for L'Hopital's rule. This is indeterminate, but it's not the form we can do anything with. We got to drive it to this. Okay. So I wanted to get through a few examples that would highlight how to use this. Again, kind of the non-intuitive aspects of infinite limits. And just one more thing before we go. Well, no, we talked about the relationship to asymptotes, both vertical and horizontal. So that will be something we see in the exercises, and I'll provide 1 or 2 written notes in this module as well. So I'm going to stop the video here. I look forward to your questions, and we'll see you in the discussion.